Hello, today we're going to review for the AP Chemistry exam by going over the free response questions from the 2021 exam. I'm recording this with students, so forgive me if there's a little extra background noise. So we'll start out with question 1. This is a long free response question. Okay, so for this question we have the weak acid methanoic acid. In water it will transfer a hydrogen ion to form hydronium and the conjugate base. Now remember, hydronium and hydrogen ions are often used interchangeably. So you can take the negative log of the hydronium concentration and get the pH of a solution. So for A, it says to write the expression for Ka, and you want to include its products over reactants. So products on the top and reactants on the bottom, but we only include aqueous or gases, so that liquid water will not be included. Just one point, make sure you write Ka equals, and then write your expression. Make sure you're using brackets for concentration. So then for B, it says calculate the pH of a 0.25 molar solution. I'm going to write the ice chart, but it's not required. And I flipped these around to make it a little easier for the ice chart. Okay, and the reason I put water on the end is because it's not involved in the equilibrium, because it's a liquid. So we have a 0.25 molar solution of that acid, and right at the instant that you mix it in water, you don't have any of this stuff. When it reaches equilibrium, then some of the acid will dissociate and some of the products will form. And because their coefficients are all 1, it does that in equal amounts. So at equilibrium, you get 0.25 minus x, x, and x. So then you would plug those into your Ka expression, including the Ka value. So 1.8 times 10 to the negative 4 is equal to, and the products are both x, and the reactant is the 0.25 minus x. Now, if you want to, you could go ahead and jump directly to this part. If you remember the pattern, whenever you have a weak acid or a weak base, it will always be x squared over 0.2, or whatever the concentration is, minus x. But if you're not sure that you're going to remember that, then just draw the ice chart. It doesn't take that much time. And then from there, you just need to simplify and solve for x. Most of the time, you can ignore this x on the bottom and just multiply both sides by 0.25 and then take the square root. Or if you have a graphing calculator, I would recommend doing the 1.8 times 10 to the negative 4 times the 0.25 minus x equals x squared. Plug both sides into your calculator to solve for x. And we get 0.0067 when we do that. That's equal to the hydronium ion concentration here. And so because that's effectively the same as hydrogen ions in your solution, you can just take the negative log of that number to get the pH, which is 2.17. That's your pH. Now this one was 2 points for B. Just 1 point for A, 2 points for B. 1 point for getting the correct value for X, and then another point for plugging it in to the pH equation. So yeah, even if you didn't quite solve for X correctly, you could still get that second point as long as you're showing your work for pH. Now for part C, it says to complete the Lewis dot diagram for the acid, show all bonding and non-bonding valence electrons. So it's good to remember that hydrogen has 1 valence electron, it's in group 1. Oxygen has 6 valence electrons, and carbon has 4. So hydrogens tend to form just 1 bond because it only has that 1 electron. Carbons tend to form 4 bonds, oxygens tend to form 2 bonds, and the other ones are lone pairs. So you already know that there's going to be 2 2 lone pairs on each of those oxygen atoms, because you will always have that on an oxygen atom. And then you want to show the bonding electrons. Now, because of the way this question was worded, you really should show the electrons instead of the lines. So in this case, I would show, you at least have 2 electrons between each atom like that, because you have to have 2 electrons shared to form a single covalent bond. But carbon tends to form 4 bonds, right? And all of the atoms need 8 electrons on it, except for hydrogen. So you need to turn this into a double bond to get 8 electrons around the carbon, 8 around the oxygen, and we already had 8 around this oxygen. And so that's what I was looking for. I believe they did give the points if you connected the dots and could just use lines, but the way this was phrased, you should really show all of the dots, all of the electrons. Okay, so then we have a different compound reacting with water, and we have a 50 milliliter sample of that compound, and it's combined with a 50 milliliter sample of the acid that we were looking at before. Now in this case, they gave us a Kb value, so we know this is a base, but we also know it's a base because the water is transferring a hydrogen to it. So the water is acting as an acid in that case. So now we need to write the balanced ionic equation for the reaction that occurs. So we have the H2NNH2, which I don't even know how I would name that, HCOH. They don't expect you to have like these acids and bases memorized. They just expect you to look at the reactions that are given and see how they react and follow that same pattern. So in this reaction, you can see the water is giving its hydrogen to the base. In this case, the acid will give its hydrogen to the base. So it will form that same conjugate acid, H2NNH3 plus, same one that we have up here. And this thing will lose the hydrogen to form just the COOH minus. Oops, I missed a plus sign somewhere. I only wrote 1 and plus sign, and this should be a positive charge, and then you should use a plus sign to make them so that they're together. And they're both weak. Okay, so you don't need to separate either one on either side of the reaction because everything that's going on is weak. Okay. And then it says, is the resulting solution acidic, basic, or neutral, and justify your answer. So the Ka value that was on the previous slide for that acid was 1.8 times 10 to the negative 4. Now they give us a Kb for the weak base. That was 1.3 times 10 to the negative 6. This acid is stronger than the base. However, right, we're reacting a 50 milliliter sample of the 0.25 molar with a 50 milliliter sample of 0.25 molar. You have equal amounts of both of those things, so they will completely react. And when you have the stronger the acid, the weaker its conjugate base. So this one is weaker. And the weaker the base, the stronger the conjugate acid. So because its conjugate acid is stronger, it's going to be acidic overall. So the best explanation for that, we'll talk about the conjugates, the strength of the conjugates, not the strength of the original acid and base. You're looking at the conjugates because they've completely reacted. So you don't have any of the original stuff anymore. You just have the conjugates. And then for part E, this time we're using a catalyst. When a catalyst is added, the reaction, this reaction occurs, okay? Is it a redox reaction, and justify your answer? Anytime you're looking at redox, you should use oxidation numbers. So elements by themselves have an oxidation number of 0. Hydrogen in a compound has a positive 1. Oxygen is -2 in a compound. And then it really doesn't matter what the carbon is. This one's +4. This one's +2. I can add. Okay. But as long as you show that one thing is changing, then you're good. So you could say, yes, it is a redox reaction because the hydrogen changes from a +1 oxidation state to a 0 oxidation state. And anytime you see an oxidation number changing, yes, it's a redox reaction. Okay, so now we're tracking the total pressure over time. And the reaction, the total pressure is monitored as shown as the graph above. I'm going to rewrite the reaction here so we can see what gases are being formed. It's this, okay, so the total pressure is monitored. The vessel originally did not contain any gas. Calculate the number of moles of CO2 produced in the reaction. Assume that the amount of CO2 dissolved in the solution is negligible. Okay. Okay, so because the reaction is forming both hydrogen gas and carbon dioxide gas, and it's producing it in a 1-to-1 ratio, I know that that 24 ATM is going to be 12 ATM from hydrogen and 12 ATM from carbon dioxide because of the 1-to-1 ratio. And the partial pressure is just dependent on the moles of the gas. They're going to have different masses, different densities, but the pressures will be the same because the moles are the same. All right. So now, calculate the number of moles of CO2 produced in the reaction. Well, we have a volume, we have our pressure, we have a temperature. We can use Pivnert. Pressure is 12, volume is 4.3, N is what we're looking for. The gas constant is 0.0821, and our temperature needs to be in Kelvin, so 298. Add 273 to 25. And then you just need to solve for N. So you get 2.1 moles there. This one tripped a lot of people up that year because they were, a lot of people plugged in the 24. But you should definitely pay attention to the actual reaction that's occurring and looking at those states. And then after the reaction has proceeded for several minutes, does the amount of catalyst increase, decrease, or remain the same? It remains the same. Catalysts are not changed or used up as a reaction occurs. Now on to question 2. This is also a long free response question. Remember, all of the long free response questions are 10 points each. So now we have silicon, and they give us the mass spectrum of a pure sample of silicon. How many protons and how many neutrons are in the nucleus of an atom of the most abundant isotope of silicon? All right, so the most abundant, we need to use a graph, so it's 28. And you guys should know, hopefully, that the mass is the total number of protons and neutrons. And so silicon on the periodic table has 14 protons. So you just need to then subtract 28 minus 14 and you'll get 14 neutrons. It's not always the same. Like if they were asking you about the least abundant, then it would be 16 neutrons. But the number of protons stays the same. And that's on the periodic table. Now, for II, write the ground state electron configuration. You always start at 1s. And s can hold 2. So 1s2, 2s2, 2p6. P can hold 6. So that brings us up to neon's configuration. We need to keep going. 3s2, and then 3p2. We only go to P2, we don't fill up the P because there's not enough electrons. We need just the 14 electrons in the neutral silicon. So that's why you would stop at 3P2. Okay, we have two compounds with silicon dioxide, and SiH4. I'm not quite sure how you name it. Silicon tetrahydride, maybe? I don't know. But the SiH4 boils, but silicon dioxide remains a solid using principles of interparticle forces, which is just intermolecular forces, explain the difference in boiling point. So SiH4, if we were to actually draw it out, would look like this, just like CH4, just like methane, because silicon's in the same group as methane. It can form 4 bonds. The only thing that holds molecules of SiH4 to each other are London dispersion forces. Because it's a completely nonpolar molecule. The difference with SiO2 is that this is one of the very few things that you need to remember is a network covalent. Okay, there's only really 2 things: silicon oxide compounds, and you don't even need to remember the ratio of silicon to oxygen. Just if you see silicon and oxygen there, you know it's network covalent because it's going to make up glass. The other one is carbon, like pure carbon. It's going to form like graphite or diamond. And so because it forms covalent bonds between molecules, those are much, much stronger than the London dispersion forces, and it's going to take significantly higher temperatures to get it to melt or boil. So really just remember carbon compounds, solid compounds that are only carbon, so graphite and diamond, and then silicon oxygen, silicon oxides, or glass, or network covalent. Now, SiH4 decomposes to form solid silicon and hydrogen gas. And it says at high temperatures, this is probably a gas too, but they won't take off points for that. If they don't tell you what it is, you're not expected to know it, except for things like water. Like you need water is a liquid at room temperature. But that's not balanced, so you would need to put a 2 there to get that to balance. The 4 hydrogens and the 4 hydrogens. Okay, and then we have a table of absolute entropies, so our S values, and explain why the entropy of the solid silicon is less than that of the hydrogen gas. So it's because silicon is a solid and hydrogen is a gas. That's what it's looking for. The gas has more entropy, it's more disorganized, more spread out. So that's why it's a higher entropy value. For part E, calculate the value in joules per mole Kelvin of delta S for the reaction. So, and this is on your formula sheet, but it's always products minus reactants for entropy. You just need to take the coefficients into account. So I would add up the 18 from the solid silicon, and I would do 2 times the 131 from the hydrogen gas. That's my products minus the SiH4, the reactants is at 205. And when you subtract that, we get 75. And it's the same unit as in your data table there, joules per mole Kelvin. Now, let's say you wrote the balanced reaction wrong. As long as you're following the reaction that you wrote in part C, you could still get the point for part E. As long as you're showing your work. Okay. Now, part F, the reaction is thermodynamically favorable. So every time you see that, thermodynamically favorable, you know that delta G is negative. And it's thermodynamically favorable at all temperatures. Ooh. Explain why the reaction occurs only at high temperatures. So it says it's favorable at all temperatures. but it only occurs sometimes. So anytime that you guys see a situation where the reaction is not occurring how you would expect, the reason is activation energy. Activation energy. And that's called kinetic control versus thermodynamic control. So it's thermodynamically favorable, but it's not favorable with kinetics unless you get to really high energy. And that's because it has to reach that activation energy barrier to get it to go. So now we have a photoelectron spectrum of pure silicon. On the spectrum, draw the missing peak that corresponds to the electrons in the 3p sublevel. So hopefully you look back to your previous answer. You already wrote the electron configuration, hopefully. 3s2, 3p2. That's what the answer was for the electron configuration. So for the 3p, we only want it to go up to 2 electrons because there's 14 total. And we want it to have a slightly lower energy, slightly lower binding energy than the 3s, because it's just slightly further away from the nucleus. So it will look like this. So to get the point, it needed to go up to the same level as the 3s and be further to the right. Remember, the one with the highest energy is always the 1s. So just pay attention to the scale. Highest energy is 1s. Okay, atomic structure, explain why the first ionization energy of germanium is lower than that of silicon. So I would always recommend when you see questions like this, you look at what's the same and what's different. So silicon has 14 protons and it's in the 3rd energy level. Germanium has 32 protons and it's in the 4th energy level. They're in, I missed a whole number there, 32 protons. It's in the 4th energy level. They're in the same group. Okay, silicon and germanium are right on top of each other in the same group. So protons aren't going to be as big of a deal because they're in different groups. If they're in the same energy level, then you need to look at protons. But since they're in different energy levels, that's the important part. So the first ionization energy of germanium is lower because its valence electrons are in a higher energy level that's further away from the nucleus. And make sure you mention that it's the valence electron too, because that's an issue that I see a lot is people will just say germanium has 4 energy levels, so it has a lower ionization energy. That's not enough. You need to say that the valence electrons experience a lower ionization energy because they're in that outermost level. It has other electrons that are closer, so you need to be specific. And then for the last part I, and this one was a really long one, a single photon with a wavelength of this many meters is absorbed by silicon. Calculate the energy. These equations are on your formula sheet. E equals hv, or that's frequency, and c equals lambda v, that's your wavelength. And again, the formulas are there, the constants are there, even what each of the variables is. It's all on your formula sheet. So I want to use this one first because of the wavelength. So c is the speed of light, 3 times 10 to the 8th. 4 times 10 to the negative 7 is our wavelength. You would solve for v, which is not on there. Okay. So let me plug it in my calculator. So I have 7.5 times 10 to the 14th for my frequency. The unit for that is inverse seconds. And then you would plug that into the other equation, E equals hv. So energy, Planck's constant is 6.63 times 10 to the negative 34th. And we plug in our frequency. And you get that the energy is 4.97 times 10 to the negative 19th. Joules for energy. Another common question they'll ask is like the energy for 1 mole of photons. That comes up a lot. Since this one said a single photon, you were good here. But if it asked for a mole of photons, you would just multiply by Avogadro's number. The 6.92 times 10 to the 23rd. So, and that is the end of question 2. This is question 3. It is the last of the long free response questions. Now, the student wants to determine the molar concentration of a copper 2 sulfate solution using 2 different procedures, precipitation and spectrophotometry. For precipitation, they add barium nitrate to the copper 2 sulfate. The reaction goes to completion and a white precipitate forms. The student filters it, dries it overnight, and they give you the data. Write a balanced ionic equation. So the barium nitrate reacts with the copper 2 sulfate, and the barium and the copper are going to swap because it's a double replacement. Sulfate has a 2 negative charge. Barium has a 2 positive charge. Copper therefore has a 2 positive charge. Nitrate is a -1 charge. So whenever you write this, you get copper with 2 nitrates and barium with the sulfate. I suggest writing like the first, like the full ionic equation off to the side, and then just write the net ionic equation in the space provided for your answer. Anything that is aqueous on both sides, this is aqueous. Sulfates are aqueous except for calcium, strontium, barium, silver, mercury, and lead. So barium sulfate is not soluble, but nitrates are soluble. So the copper winds up being a spectator ion, and the nitrate winds up being a spectator ion. And so your net ionic equation, you have your barium ions reacting with your sulfate ions to form barium sulfate solid, which is that white precipitate. And then we need to calculate the moles of precipitate formed. So we have our filter paper with the dried precipitate, and then we have just the filter paper. So you would subtract to find just the grams of the precipitate, which is 0.372 grams. And then now that you have grams, you can change grams to moles using the molar mass. So the molar mass of barium sulfate is 233.39 grams per mole. So when you divide, you get the moles of the barium sulfate. That one was actually 2 points, one for knowing that you have to subtract out the filter paper mass, and then the second point for using the molar mass correctly. I'm running out of space. Calculate the molarity of the original copper sulfate solution. So this is a 1-to-1 relationship here between the barium sulfate and then the copper 2 sulfate. So that makes it really easy. I'm going to kind of squeeze it in over here. I know I have 0.00159 moles then of copper 2 sulfate because it's equal. It's a 1-to-1 relationship. To find molarity, I need to do moles divided by liters. So I have 50 milliliters, that's 0.05 liters. And when you divide, you get 0.0318 molar for C. Okay, so then they did that precipitation experiment. Now for the spectrophotometry experiment, they make a standard curve. They use 0.1 molar solution of copper 2 sulfate to make 3 more solutions of known concentration. Calculate the volume of 0.1 molar copper 2 sulfate to make 50 milliliters of 0.05 molar. So this is a dilution. because you're going from 0.1 molar to 0.05 molar, so you're diluting it, making it less concentrated. So you can use M1V1 equals M2V2. We don't know how much of the original solution we need, but we know that we want 0.05 molar and 50 milliliters. So when you solve, you should get 25 for V1, 25 milliliters of your 0.1 molar solution. Then you need to briefly describe the procedure the student should follow to make the solution using the 0.1 molar stock, a volumetric flask, and other standard laboratory equipment. Assume all safety precautions will be taken. This pops up a lot, how to make solutions properly. So what you would need to do is to measure 25 milliliters of the 0.1 molar solution. You could measure it in a graduated cylinder. You could use a pipette, you could use a burette, but you'd want to try to find something that can measure exactly 25 milliliters of that stuff. Then you will put that into the 50 milliliter volumetric flask. Once you transfer it in, then you will slowly add deionized water while stirring till it reaches that 50 milliliter line. And so that's really your standard procedure. Some kind of equipment that can measure the exact amount you need, adding it to your flask, filling the flask with deionized water while stirring. If you're making it from a solid, you would just weigh out the exact amount of solid, put that in the flask, and slowly add it. So here's the standard curve, or the calibration curve. Absorbance is on the y-axis, concentrations on the x-axis, and then it says the absorbance is 0.219, determine the molarity of the solution. 0.219. So you can really just estimate on the graph here. The absorbance is 0.219, 0.2, that's 0.3, so like 0.21, and then you just trace over, I don't know, so like 0.035-ish. They'll usually accept a range of values. But that's it. It's just asking you to read the graph. Let's see what the scoring guidelines say. Yeah, it says anywhere from between 0.032 to 0.038. As long as you're somewhere in that range, you're good. Okay, the second student performs the same experiment. There's some water in the cuvette before the student adds the copper 2 sulfate. Will this result in a concentration that is greater than, less than, or equal to the concentration determined in part F? Well, if you have extra water, that's going to make the measured concentration less. Right? So the absorbance will be lower, and your concentration will then be lower as well. Because there's more water, it will block less light. This is question 4. It is the first of the short free response questions. It's worth 4 points. Okay, so student investigates a reaction using hand warmers represented above. So this one is the iron reacting with oxygen in the air. So actually you can buy very similar ones at the store. They're just like heating pads that as soon as you like open the package and it reacts with oxygen in the air, it's going to start to heat up. It's very cool. Anyway, the student mixes the iron with catalyst and sand in a small open container. The student measures the temperature of the mixture as the reaction proceeds. So they give you temperature over time. The mixtures, which is the iron, catalyst, and sand, has a total mass of 15 grams and a specific heat capacity of 0.72. Calculate the heat absorbed from 0 minutes to 4 minutes. So we have a specific heat capacity. You're probably going to need to use Q equals MC delta T. That's the only equation that we have for this class with specific heat capacity. So we're looking for heat. The mass was 15 grams. Specific heat capacity is 0.72. We just need to use the change in temperature from 0 to 4, which I'm going to quick subtract. So 17.4 is my change in temperature. And then so my value for Q is 190. And the unit there is joules because of the joules in your specific heat capacity formula there. Now for part B, it says to calculate the mass in grams that reacted to generate the amount of heat calculated in part A. So it formed 190 joules, right? They also gave you the delta H for the reaction, and that was at the beginning. Let me write it down. It was negative 1650 kilojoules per mole. And that was in right up at the beginning of the question. So what I can do is I can change joules to kilojoules, so 0.190 kilojoules. And then from there, if I take this heat, 1650 kilojoules per mole, that way I cancel out the kilojoules, right? I'm going to go ahead and actually, instead of using the negative sign, I'm going to assume it's a magnitude. Because you can't have like a negative number of grams of things. So you can just use the absolute value there. Now, it's not asking for moles, it's asking for iron in grams. So let me rewrite the equation actually. So the balanced equation is 4 iron plus 3 oxygen yields 2 Fe2O3. So that's at the beginning of the whole question. And that's important because this mole in your heat is the moles of reaction. And for every 1 reaction that happens, you have 4 irons that are used up. And then we can use the mass of iron, which is 55.85 grams per mole. So our kilojoules canceled, our moles cancel, the reaction cancels, and then we're left with iron, grams of iron. So you would do 0.190 divided by 1650 times 4 times 55.85. And you get a very small number of moles actually, 0.00012 moles of iron. Which makes sense because this number is very small in comparison to the heat of reaction. Okay, in the second experiment, the student uses twice the mass of iron as calculated in part B. Oh, I'm sorry, this is the wrong number. That's the number of moles we need. I'm just not doing well in this question. 0.027 grams of iron. There we go, that makes more sense. It's like, that's really small. Anyway, so that's the grams. Student uses twice the mass of iron that was calculated in part B, but the same mass of sand as in the first experiment. Would the maximum temperature reached in the second experiment be greater than, less than, or equal to the maximum temperature in the first experiment, and justify your answer? So the sand is really just there to hold the heat, right? There's also a catalyst, but like that's where the reaction is happening. The sand itself is staying the same, which is fine. You're using twice as much iron. The iron is what's reacting with the air to form the heat. So the heat that is released is going to be greater. So again, because you're changing the thing that is actually producing the heat when it reacts, that's why you're going to have more heat produced, so a greater temperature. If the sand was changed but the iron was kept the same, you wouldn't see it. You might see a lower temperature because you'd have more sand that you need to change the temperature of, but okay, so that was it for that question. Now let's look at the next short free response question, question 5. This one is a redox question, and I can tell right away because they gave us half reactions with the voltage. Okay, so molten magnesium chloride can be decomposed into its elements if a sufficient voltage is applied. So this one, they give us a power source, so that's how you know it's electrolysis. The products of the reaction are liquid magnesium and chlorine gas. A simplified representation of the cell is shown above, and the reduction half reactions are given in the table. Draw an arrow on the diagram to show the direction of electron flow through the external circuit. The easiest way, I think, to figure this out is to write the reaction based on the data that they give you in the question. Magnesium chloride decomposes into its elements to form magnesium and chloride gas. So if you use your redox, if you use your oxidation numbers, these are both 0 because they're elements by themselves. Magnesium in the compound is the same as its charge, which is +2, and chlorine is -1 because there's 2 of them to cancel out the magnesium. So the magnesium goes from +2 to 0. The magnesium must be gaining electrons because it goes from +2 to 0. So the magnesium, which is here, is gaining electrons. The electrons must be going towards the magnesium. Okay, and then it says, would an applied voltage of 2 volts be sufficient for the reaction to occur, and support your claim with a calculation? Okay, well, this reaction is the same as it's written here, right? The magnesium ions are changing into solid magnesium. But this one is the opposite. We want the chlorine gas being formed, so let's go ahead and flip that. And so when you flip the reaction, you'll change the sign. So now it's an oxidation half reaction. And if I were to then put these two reactions together to form my overall, the electrons would cancel and you'd have to add up those voltages. So I'm going to do that in my calculator. So the total would be -3.73. That means I would have to use at least 3.73 volts to get it to work. So is a voltage of 2 volts sufficient? No. You would need at least 3.73 volts to it. And then the last part of this question, if the current is kept at a constant 5 amps, how many seconds does it take to produce 2 grams of magnesium at the cathode? So amps you should know is equal to coulombs per second. The equation is I = Q/T, but I think it's much more useful for you to remember it like this because it actually gives you the units that you need to calculate the amps, or vice versa. So let's start out with the grams. Anytime you see grams, you should change grams to moles using the molar mass of magnesium. Okay, and then magnesium, we saw that from the previous slide, but it's using 2 electrons, right? So for every 1 magnesium, we have 2 electrons. And that's because I didn't put the substance here, but the magnesium can cancel. And now we have moles of electrons. From there, we can use Faraday's constant. Coulombs per mole of electrons. So moles of electrons cancel. So now I can find the coulombs that I need for this. So 2 that's the charge, the quantity of charge. So now if I know it's 5 amps, and I know I need 15,882 coulombs, I can solve for the seconds. And so 3,176 seconds. Really, if we're using 3 sig figs, it would be, what, 80? Question 6 is also a short free response. Remember, all of the short free response questions are 4 points. Okay, so calcium sulfate and lead 2 sulfate Student has samples of both compounds, which are white powders. Student tests the electrical conductivity of each solid and observes that neither solid conducts electricity. Describe the structures of the solids that account for their inability to conduct electricity. It's because they're ionic compounds. Okay. You have a metal with one or more nonmetal, it's ionic. Ionic compounds do not conduct electricity as solids because their ions are trapped in a lattice and they can't move. And so that would be enough for that explanation. Metals, on the other hand, pure metals can conduct electricity as a solid because their electrons are free to move. But that does not happen with ionic compounds. So those ions are fixed in that lattice structure. Okay, so we've got calcium sulfate in a beaker containing 100 milliliters of water, excess lead 2 sulfate in another beaker containing 100 milliliters of water. They stir the contents, measure the electrical conductivity in each. Student observes that the conductivity of the solution in the beaker containing calcium sulfate is higher than the conductivity of the solution containing lead 2 sulfate. So which compound is more soluble? Justify your answer based on the results. The calcium sulfate is going to be more soluble because it has a higher conductivity. It must be producing more ions. So it must be breaking down into those ions more. That's all. Okay, so the left side of the diagram shows a particular representation of the beaker containing calcium sulfate. And we want to draw the representation of the lead 2 sulfate and the ions dissolved on the right. So we really want it to be less conductive, so you want to see fewer ions here. So you try to draw it in the same way as much as possible, but I'm going to make there be more solid particles. And then you should try to shade in the positive ones because that's how they did it on the key. And you will have fewer that are ions. That's it. If you had done like 12 solid particles and just 2 ion particles, that's fine too. But you did need to show at least some of them dissolving, but more of them are solid in your picture. Okay. And then for the last part for this question, the student attempts to increase the solubility of calcium sulfate by adding 10 milliliters of sulfuric acid. Observes that additional precipitate forms and explain. So I'm going to explain this by writing out the solubility expression, or the solubility reaction, really. Okay. So you could write a KSP expression for this reaction, but you don't really need to for this question. But we're adding in sulfuric acid. That's a strong acid. It's going to break down into hydrogen ions and sulfate ions. That means you have excess sulfate ions in the solution. According to Le Chatelier's principle, if I add in something, it's going to try to use that up, so it's going to shift towards the reactant side to produce additional precipitate. You really should, if you're going to use that as your explanation, you should use Le Chatelier's principle, like use the name. There's only 2 names you really need to know, Coulomb and Le Chatelier. So if you're talking about shifting it, you really should say according to Le Chatelier's principle, somewhere in there. And this is the last question on the exam. It's your last short for your response question, question 7. So the cylinder contains 0.325 moles of O2. It's a movable piston. That means the pressure is going to stay constant and just the volume will change. Cylinder has a volume of 7.95 liters at this temperature and pressure. Calculate the density in grams per liter under these conditions. There's a couple ways you could do this. I think the quickest way is using the density equation. Density equals PM over RT, but that's not on your equation sheet. So that might be one that you remember for the test. Or you could use PivNert to find grams I'm sorry, well, you use Pivnert to find moles, and then change moles to grams. And then you would divide by the liters to get the density. But density, I think, is a little easier this way. Density goes PM over RT, so you would do the pressure, it's 1 atm. M is molar mass here. So the molar mass of oxygen is 32. Our gas constant, 0.0821, and our temperature needs to be in Kelvin always. So then you would multiply and divide. And we get that the density is 1.31. It's a weird decimal. Grams per liter. You'd get the same answer either way. It's just Pivnert and then to grams and then to density. It just takes a little longer. Anyway, so we're changing the density. We push down on the piston, close the valve again. Temperature of the gas remains constant. It's because the temperature is constant, right? Temperature is staying the same. And because it's a movable piston, our pressure is also staying the same. So even though we're releasing some of the moles of the gas, the volume is also decreasing in order to keep the pressure at the same level. And so because of that, it's going to keep the density the same. Okay, so we're going to cool the gas down to -55, which causes the volume to decrease. Using a kinetic molecular theory, explain why the volume decreases when the temperature decreases. Really, that's just at lower temperatures, the particles have less kinetic energy, so they're moving slower and cannot spread out as far at those low temperatures. That's it. Anytime you see kinetic molecular theory, you want to talk about just the movement of the particles. Okay, further cools the cylinder to -180, observes that the measured volume is smaller than the volume calculated by the ideal gas law, assume all of the equipment is functioning properly, explain why the measured volume of O2 is smaller than the calculated volume. There's two assumptions in the ideal gas law. There are no intermolecular forces, and that the actual particles themselves have a negligible volume. So you could use either of those to explain a deviation from the ideal gas law. In this case, I would probably say the easier way to explain it is by saying at -180, you're going to form intermolecular forces. So that's going to attract the particles to each other and decrease the volume because they're stuck together. But those are the two really possible answers for any deviations from ideal gas law.